So I have a bunch of slides, but I'd really like, maybe I'll close this door. Maybe not. But the hope is that it's interactive and particularly asks questions, especially if I say something you don't quite understand, maybe I can explain it in a different way. So I'm going to talk really about two topics. I'm going to talk about black holes, but also gamma ray bursts. So I want to give initially some initial concepts to make sure we're all on the same page. Talk about these gamma ray bursts, what they are, how do we find them, black holes, explain why they're so powerful, and then tell you about how black holes and gamma ray bursts are connected together. So to get us all on the same page, just some definitions. You know that we're on a planet, we go around the sun, but this sun is just one star of nearly 100 billion that is in a large thing called the galaxy. Our galaxy is called the Milky Way. We're very blessed here in Santa Fe, where almost every night you can go up and look and you see this strip of stars across the sky. That's the Milky Way. We're sort of in the edge. We're out here. We sort of, that strip is because it's like a flat pinwheel, and you can sort of look along the edge of it as you look in the Milky Way. But this is just one galaxy. Here is 10 to 100 billion stars, but that's just one of nearly 10 to 100 billion galaxies. This is one of my favorite pictures. This is the Deep Sky Survey from Hubble, and what Hubble did is they went to a part of the sky where there are very few stars you can see from our galaxy. In fact, I think this is the only star in this picture. Everything else on here is a galaxy. So you can see these nice galaxies, but this is a galaxy, that's a galaxy, that little blip right there is a galaxy of 100 billion stars. Okay? So the universe is huge, and everywhere you look you see these galaxies. And this is only a very small part of the sky. If you take a dime and you hold it up at your arm's length, what you're really looking through is like Roosevelt's eye. That's how small of an area you're looking at when you see a picture like this. So the whole universe is filled with these galaxies. And all of these galaxies, all of this, burst out of the vacuum 13.7 billion years ago in an event we call the Big Bang. So the whole universe expanded out of a tiny spot. In fact, that's the actual size of the Big Bang. Okay? That's about the size of the Big Bang. About 1/billionth of a second after the Big Bang, that's how big all those galaxies and the whole sky, all that material was in a little spot about that big. And the other thing is I'll be talking about gamma rays. So what are gamma rays? Well, gamma rays are really just high energy X-rays. In fact, all these things are all the same phenomena. Sorry. Here's some seats. All these things are the same phenomena. It's all what we call light, except our eyes can only see this visible light, but radio waves and ultraviolet and the microwaves in our ovens, medical X-rays and gamma rays are all the same, exactly the same phenomena, except that they different energy associated with it, different frequency. So the gamma rays are very high frequency, very high energy. This is the light that we see. So that's sort of give you an idea of some of the things that I'll be talking about. So the first thing I want to talk about are these gamma ray bursts, what they look like, how we find them, what would happen if you put a gamma ray detector in space. And in fact, Los Alamos did this in the late 60s. We had the responsibility of enforcing a treaty that we had with the Russians. We said, hey, nobody's going to set off nuclear weapons in space. And we had the responsibility to put sensors up there to make sure that they don't set off nuclear weapons in space. Well, a nuclear weapon in space, when it blows up, produces a big burst of gamma rays. So, and we figured, oh, this is going to be simple because nothing in the universe makes bursts of gamma rays. Okay, so we'll put these detectors up there and we don't have to worry about false alarms or anything like that. Well, what happens if you put a gamma ray detector in space? Here is a function of time, and here is number of gamma rays you see, and what you see is just a hiss. There's just a background hiss, just like on a radio, but then about once a day you get a blip. And in fact, sometimes you get a bunch of blips, and then it turns off. And this was quite surprising to us because we really just expected, just to see a hiss, unless somebody set off a nuclear weapon. And these things don't look like nuclear weapons at all. There was never any confusion on that. So this was the discovery of these gamma ray bursts, that we realized that there's something out there that is making these really complex. I mean, what's bursting? Why is it doing that? The other thing to note is how bright they are. And this is the number of gamma rays that you see. Here it says about 3,000 gamma rays per second or so. And here's what all the rest of the whole universe is doing. So this is like all of a sudden you saw a very bright light here, okay, maybe coming through those windows. The first thing you'd assume is, well, it's probably close by. I mean, if it blinds you, it's probably a close by light. And that's what we assumed about these events, that they were reasonably close by, maybe 10,000 light years away or so, but certainly within our own galaxy. So in 1991, NASA launched an experiment called BATSI. And here it is being launched by the space shuttle. This thing is about the size of a school bus or so. It actually carries 3 or 4 experiments. But BATSI is sort of these detectors are on the corners. And they were capable of finding 1 gamma ray burst per day. And what it could do is sort of find crudely where they're located. I mean, it can't tell with great accuracy, but it'd be able to say, roughly within a few degrees, which is maybe 10 times the size of the moon, where they are coming from. And of course, we thought we understood these things and we knew exactly what to expect when we did this experiment. We expected to see a map like this. If you take a map of the Earth, it's round, but you can flatten it out and make it flat. So you can take a map of the sky and you can flatten it out. And if you did that, it would look like this. This is a very, very small fraction of the 10 billion stars that are in our galaxy, because the whole thing would just be all white. But here's the Milky Way. In fact, if you go out at night, this is what you see across the sky. And this is exactly what we expected to see where these gamma ray bursts were coming from. Because we figured they were maybe 10,000 light years away. So they did this experiment, and instead they found they were completely uniformly distributed. Completely uniform. No association at all with things in our galaxy. In fact, no association with nearby galaxies. In fact, no association even with large clusters of galaxies. That means these things must be very far away. The implication of this is that these objects are extremely far away. You have to remember that light that came through the window nearly blinded us. And now this evidence says these things are extremely far away. So, we tried to understand that. Now, actually, I'd like to stop right now and ask if you have any questions about what I've said so far. Anything I can clarify? Yes?
What does plus 90 mean?
This is degrees, so this is a map of the sky. So this is plus 90 degrees latitude. And this goes plus or minus, I guess, 180 degrees longitude, because it's a map of the sky. Yes?
What was outside the small dot that was a second after the Big Bang? What was?
Well, space itself, okay? The Big Bang actually expanded space. Oh, yes, I need to repeat the question. The question was, on the Big Bang, what was outside when the Big Bang went off? The Big Bang went off in a vacuum, okay? In fact, the vacuum, just like in this room, I mean, right here in front of my hand, it's mostly vacuum. There's a few atoms. In fact, my body is mostly vacuum, okay? And there's a few atoms here, but this space, any space, we think can produce a black hole, can produce a Big Bang. It's just very rare. So that one happened. So the space itself then expanded. So what was around it? Normal space like this.
How fast did it come to its, or is it still expanding?
Oh, it's still expanding. In fact, it's accelerating. And initially, it was expanding very close to the speed of light. Yes, there was a question back here. Yes?
Is there any evidence that there's only been one Big Bang and our universe is the only universe?
Well, there's a lot of thought now that there might be multiple universes. And some of that comes because we're beginning to realize how delicately balanced this is. I mean, it's been expanding for 13.7 billion years, and yet, I mean, if the universe was a little bit smaller, the Big Bang was a little bit smaller, it would have collapsed on itself long ago. If it was much bigger, it would have expanded out. how come it has sort of this exact balance? So the implication is that there's lots of these. We just happen to live in one that's long-lived, long enough that people can evolve to look up and go, what's that? Yes, another question.
What's the significance of different colors?
This might be slightly different types of gamma ray bursts. Slightly different, the question is, what are the significance of the colors? I think it's, this is an old figure and my memory is going. I think it's slightly different types as to whether it has lots of pulses in it, whether it's a short burst, a long burst. Because gamma ray bursts, no two of them look alike. Why don't I take one more question in the back there? Yes?
You said that the universe is still expanding and that the speed at which it's expanding is increasing. Why is it increasing?
The question was, why is the universe still expanding? Why is the speed increasing? And this is only a discovery that we've made in the past decade or so, mostly with the Hubble Space Telescope. And we don't know why. We can give it a name. We give it the name dark energy, okay? But beyond that, we don't really know why. And it was unexpected. I mean, everybody, because we discovered that 70% of the energy in the universe is actually tied up with this, expansion. And we don't really know what's causing it. 70% of the universe is dark energy, and we don't know what's causing it. Interestingly, the rest of the material, about 30%, we can't really explain 25% of that. What you see is actually only 5%. We've only explained the existence of about 5% of the universe, of the matter in the, of the energy in the universe. Okay, why don't I go on? The idea here is that this experiment was done, and we expected to see all the gamma ray bursts lined up here. Instead, we see them very uniformly distributed, and nothing is very uniformly distributed except very far away galaxies. So if we look at one particular red dot like this, and we blow it up, it's actually about 3 degrees, and the moon is a half a degree in size. So this is a rather large area. But even if we look at 1/100,000th of that area, what we see is all these galaxies. Okay? And so now the question is, well, which one made the gamma ray burst? Okay? And so that's very challenging now to figure out which one of these made that gamma ray burst, because we're trying to figure out how far away they are. Once we know how far away they are, then we know how much energy they're producing, and we can start working on models to try to explain what makes these things tick. Mm-hmm. So now one of the problems is that gamma ray burst, like I said, if you've seen one, you've seen one. They all look different. Mm-hmm. Some last only 1/100th of a second, a few milliseconds. Some last most of them last about 10 seconds, 10, 20 seconds. There are some that last hundreds of seconds. But even at 100 seconds, you can't have humans involved in this. Okay? I mean, if you have a satellite, you build a satellite, you get the data down, you can't have a human look at it and go, oh, maybe this is what we should do next. Okay? I mean, first of all, we had to throw away the humans, and we had to build completely robotic instruments to detect these gamma ray bursts, with the primary goal of trying to find out what galaxy did they come from. So we've built satellites like this. This is called the SWIFT satellite, and it's quite large. Here's some people. And this particular thing right here is the Los Alamos telescope that was built. And then there's 2 other telescopes. This does gamma rays. There's an X-ray telescope and an optical telescope. And this is getting ready for launch at the Kennedy Space Center in 2004. So, in fact, this is great fun. Here the satellite is in what's called a shroud, the sort of the nose cone of the rocket. Here's a person down here, making sure it's ready to go. Launches are great fun. Okay, I mean, launches are just fantastic. I think I was about less than 2 miles away from this when it went up. Launches are great. And then here's a sort of an artist's conception of this satellite in space. This is the gamma ray instrument. And by the way, this is for students here. So this imaging technique was actually a process that I invented while I was a student. And now it's used in a lot of satellites, including the Swift satellite. But this is the gamma ray system. There's an X-ray telescope and an optical telescope. Now we said the gamma ray bursts are just too fast, 10, 20 seconds. So everything has to be robotic. So the gamma ray telescope figures out, hey, a gamma ray burst just happened. On board the satellite, it processes all this data and figures out which direction the gamma ray burst came from. And then it tells the satellite, go point in that direction. And it does this all completely by itself because it wants to point these other telescopes to it to try to get another image of it to try to pin down what direction they're coming from. Of course, if you want to have a question, just raise your hand. I'll stop in a moment and ask for some more. So, so how do we use this? The satellite figures out where the gamma ray burst is located, and the satellite starts to spin over to look at it. And it takes the satellite about 70 seconds to spin over and look at it. That's a long time. These things only last 30 seconds on average. So it also sends information down to the ground. Now, a satellite in space doesn't have an Earth to push against, so it has a little bit hard time turning itself to point in this new direction. So, but it can get the signal down to the ground and onto the internet and off to observatories all over the world. And in fact, that signal can get here in about 6 or 7 seconds. So the ground actually can start pointing to these gamma ray bursts before the satellite can. A series of robotic telescopes have been built all over the world in order to respond to these gamma ray bursts from the Swift satellite. And we have built a large number of satellites, and they're all up in the Jemez Mountains, up in Fenton Hill. And we build all sorts of different types of satellites, but the whole idea is to try to watch as much of the sky as possible very quickly and be able to robotically move and look at it. These telescopes are the fastest moving telescopes in the world. In fact, the first time we turned it on, fortunately we weren't standing near it because it not only whipped over to look at the first position, it burned the gears. Okay, so we said, okay, let's dial this down a little bit. Maybe we can, spend a second getting there, not just a half a second, getting over there. But we've built a whole bunch of instruments in order to pull all these pieces together to have the satellite detect that a gamma ray burst has happened. It sees it in the gamma rays. It locates it. It tells tells the rest of the satellite where to point to. Tells the ground, and then besides our instruments on the ground, there's probably 20 other sites around the world that have telescopes that can go and try to chase these. Although we certainly by far have the most number of telescopes than any other site. Typically, you just have one telescope. We have more than 50 up at Benton Hill. Okay, so at this point here, I'd like to stop and ask if anybody has any questions. Yes?
Gamma rays aren't seen by the human eye, so the satellites only track the location of the gamma ray burst, or do they actually take a picture of it?
Well, they take the satellite instruments can see in gamma rays and X-rays, so those instruments do take a picture of the sky in gamma rays and take a picture of the sky in X-rays. And we determine the location from that. Other questions?
You're leading up to something.
Yes. Yes.
Why do, this sounds strange, but why do we care about gamma rays?
Why do we care? We should all love gamma rays. They are our friends. Well,
What are they leading us to in terms of information?
well, as they don't help us grow better corn in Alaska, okay? but they're very important. The gamma ray bursts will turn out to be very important, certainly in astrophysics, because They occur so far away, they actually light up the entire universe, and we can see how the universe has evolved. Plus, so, you know, to understand them, then, I mean, many times in astrophysics, we're trying to say, well, what makes that tick? And the only result of that is now we know what makes those tick. Gamma ray bursts are different because they tell us how black holes work, they tell us how the universe has evolved, they tell us a lot about the early universe, because I'll show later, these are the furthest objects we've ever seen in the entire universe. So they're actually connected to many other topics in physics, but also all this technology of how do you have completely robotic systems where there's no humans at all in the loop, where you have satellites connected to telescopes, who are, actually we call these systems thinking telescopes. They sort of think and realize, okay, what should I really do now? Okay, and the same thing with our satellites. I mean, they really have a lot of very complex software in them that's, you know, trying to make the judgment as to what to do best now. And so that's a technology that we have then applied to many other problems here on Earth. Yes?
What's the speed that gamma rays travel at?
They are light, so they travel at the speed of light. Yes?
What would happen if a nuke went off in space?
What would happen what?
What would happen if a nuke went off in space?
What would happen if a nuclear weapon went off in space?
Yes.
Yes. Well, first of all, there'd be a big burst of gamma rays and X-rays. Second, we not only build these instruments, but Los Alamos also builds instruments. We put them on every GPS satellite. We put them on other satellites in order to detect them, so we would know where it occurred. And part of the purpose of that is to try to identify who did it, so we can know who violated the treaties or who is attacking us. But also, if a nuclear weapon went off in space, in a matter of a month or so, would wipe out all our satellites. Okay, because it produced artificial radiation belts that would produce too much radiation for almost all satellites up there, and we'd lose MTV very quickly. Yes?
But I thought that we did detonate nuclear in the Van Allen belt in the 50s.
Yeah, it wasn't as high as the Van Allen belt. They only went up to about 200 kilometers. So, in fact, there were very few satellites up there then, too. So those high altitude tests, I don't know if they wiped out any satellites. There were very few up there. But if we repeated that test today, we'd be wiping out a lot of satellites. And that's one of the reasons why we don't want anybody setting off nuclear weapons in space. Yes?
I actually had a question about the detection. You said that it can detect gamma ray bursts inwards, so it must have 360 degrees.
No. BATSI had 360-degree capability. This satellite looks at something about like this big here. Okay, and it finds the gamma ray burst in that, so we don't see them all. So the idea was, the strategy behind this experiment was to don't try to find all the gamma ray bursts that are happening, but the ones you do find, you do a great job on. So we see about 110 gamma ray bursts per year, whereas BATSI saw about 380 gamma ray bursts per year. But it's all because, you know, we wanted to just study those. Okay, any other questions? Okay.
I have one.
Yes?
What is the highest level of magnification that a telescope has on Earth?
On Earth?
Yes.
Well, I'm not sure. That would be some of the big 10-meter telescopes. Actually, and I assume you mean optical telescopes. They now have these Gemini telescopes, which are actually two sort of stereo telescopes, and they can do very clever things in the software and see. So I think they have a resolution of maybe 1/10 of an arc second. But on Earth, the atmosphere prevents you from getting any better resolution, although we put these all on very high mountains. It's one thing we do. Okay, so let me show you what we've seen from these things, okay? These things look in a big part of the sky, and here is a short little movie. This is just 6 frames, 6 pictures over 10 minutes of a small piece of the sky, because we can actually record about 100 times this at any one moment. And this is the 6 frames, so you see in frame 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. You know, so just like these political commercials on television, you just see it over and over and over again. Okay? And it's over 10 minutes, and there's, you know, you can have slight changes in clouds during that time. and there's some things that are happening. For example, here is a meteor that went through the field of view. Some things are just distortions in the camera. Radiation causes what we call a hot pixel, and it looks like it turned on and turned off, but really it's just noise in the sensor. This is an asteroid. Over those 10 minutes, that asteroid moved a little bit, and we can see that it moved a little bit. But right here is something new. Right there is, here's a star that turned on and turned off over 10 minutes. And it's in the location, in the direction that these satellites said that's where I saw the gamma ray burst come from.
So that's not a star?
Depends on your definition. It's not one of these type of stars here. I mean, it's quite different. Let me just call it a gamma ray burst for now. Okay. But it also told us that the gamma ray bursts don't just emit in the gamma rays, they also emit in the optical light. Okay. This is great, because now what we can do is we can go to the Hubble telescope and say, Hubble, please look in that direction. Okay. And in particular, we're going to look to see if any galaxy changed, because galaxies don't change. Okay, I mean, they're huge. They're 100 billion stars. So, you can't change one star out of 100 billion and get some sort of a change. So galaxies should all look the same. Yes?
Along the right edge in the middle, the thing that has something coming out of the bottom and the top, is that a quasar or something?
There's no quasars can be seen here. Are you looking at this? Or yes? This is a particularly bright star, and so it has distortions in the lenses that are making that, that little structure. So that's not jets. That's not jets coming out of that star. Everything on here is a star in our Milky Way, except this thing will turn out not to be. Yes?
What's causing it to pulse?
Well, it's turning on and turning off. This is a movie. You've seen the same 6 pictures over and over again, but it turned on and turned off. So it's not pulsing.
It's not actually doing that.
Well, it turned on and then turned off, but I'm showing you that over and over and over again, so it looks, and it stayed off. It stayed off. Turned on once, turned off.
Do you think it was a galaxy?
Well, I'm going to show you why in a moment, but we went to Hubble. We got Hubble to look at this, and of course, if you take a picture of Hubble, what you see is the same picture I keep showing you, lots and lots of galaxies. But in this case, Hubble would take a big picture like this, and then take one the next day and the next day and the next day and see if anything changed. Okay? And sure enough, here I've circled, not the real one because I don't have that real picture, but one galaxy changed so that here'd be a close-up of the Hubble data. All these are galaxies, but that galaxy, here it is here, grew a bright spot that faded away. Okay, and this has never been seen before. Like I said, galaxies don't change. Okay, but we discovered no, they do. They do when they have a gamma ray burst. So right here, here's some object that turned on and turned off. Now, once you find the galaxy, there's lots of ways of looking at that galaxy and measuring how far away it is from us. Primarily because the whole universe is expanding. So the ones that are further away look like they're moving faster, and there's sort of a Doppler shift in their light. So you can measure that Doppler shift and figure out how far away they are. And we found out that this one is 12 billion light years away. Okay. Now, the universe is only 13.7 billion years old. Okay, so this is a very, very far away galaxy. And this must be a very, very bright light. Okay, I mean, we can't see any galaxies from the Earth with your eye. You can't see any galaxies. Here apparently is one star that somehow was bright enough to be seen, a single star bright enough to be seen from 12 billion light years away. So they're incredibly, incredibly bright. And that was sort of the next frontier, is to try to explain why are they so bright. I thought I was going to say something else about this galaxy. but I don't remember it. Any quick questions on this? Yes?
What is that unit of measurement?
A billion light years?
The white bars.
Oh, that's 1 arc second. Yeah. So it's a measure, that's how big on the sky you're looking at, which is a very, very, very small little spot on the sky. Okay. Let me go on. So you need a huge reservoir of energy in order to power this thing. I mean, they're billions of light years away, and yet we can still see them. Well, one way of looking at this is being reminded of Einstein's equation that E equals mc squared, which is really a very simple equation. It means that matter can be turned into, well, a lot of energy. C is a big number, and c squared is even a bigger number. So this says any mass, like me or anything, can be turned into energy. Now, for a nuclear weapon, when a nuclear bomb goes off, it converts about 1 gram, which may be about the weight of 1 raisin, into energy. So if I had a raisin here, and if I could figure out how to convert that from mass into energy, we'd make Santa Fe a big crater. Okay? There's an incredible amount of energy that is being stored in just normal mass, if you can figure out how to convert it, which we do in, for example, a nuclear bomb. So the question is, given this background, how much energy, how much mass do you think we have to convert in order to see something 12 billion light years away? 100 raisins? 1,000 raisins? Anybody have a guess? More. Somebody says more. Plenty, yes, plenty. Okay. Well, actually it takes 400,000 Earths converted directly into energy in order to give you something bright enough to be seen from 12 billion light years away. So somehow this star is figuring out how to convert a huge amount of energy directly from mass into energy. And the question is, how did it figure out how to do that? Or can we figure out how it did that?
And the energy is in gamma rays.
And the energy is in gamma rays. Yep. Almost all the energy comes out in gamma rays.
Is the star blowing itself up? Is it destroying
Yes,
itself?
it is. It is destroying itself. In fact, I'll go over how it destroys itself. Okay. Well, so where can we get that much energy? Well, one clue is that all of the brightest objects in the universe are black holes. Okay? That anytime you see something very, very bright, it's a black hole. And I'll explain why. So we want to now talk about black holes, what makes black holes, and it's going to be, gravity is going to drive the evolution of stars to make black holes. So we're going to talk about black holes, why they're so powerful, how stars evolve, how does gravity work, and why black holes are so bright. That's not the order I'm going to speak in, but that's the topics. Well, first of all, you have to understand gravity some. And gravity by far is the most important force, even though it's the weakest force, it's the most important force in astrophysics. Everything in the universe either has mass, that is, has weight, or it's light. So everything with mass pulls on everything else with mass. So I have mass, you have mass, so right now you and I are trying to pull each other together because both have mass. Now I don't particularly feel him pulling because Earth is a lot bigger than he is. So I feel like I'm being pulled towards the Earth. Light is all these things that we see, X-rays, radio waves, microwaves, ultraviolet, and light can be the E in E equals mc squared, and m is the mass. So stars actually have a life and death, and they evolve. I don't want to spend too much time on this, but you start out maybe with a whole bunch of gas and gas, which all has mass, so it pulls itself together into stars. The stars turn on. The stars burn. Effectively, they do nuclear burning. They convert hydrogen into helium, helium into carbon, carbon into other things like silicon, and then finally they reach iron. And iron is the most stable element. Once you reach iron, you can't put things together to make more energy. If you have something heavier, like uranium, you can split it apart, get energy. If you have things lighter than iron, you can put them together and get energy. But once you have iron, there's no more source of energy. Yes?
Are you saying that helium, et cetera, transmutes to each different element in the periodic table all the way to iron?
Yes. Transmute is not quite the right term. They join together. You put 3 heliums together and you got a carbon.
Okay.
Put another one together, I think you got, I don't know, whatever comes next for later. But what happens is that gravity is pulling these things. There's this relentless force of gravity pulling together these stars. And the only thing that's stopping gravity is that there's a source of pressure from the heat being made by this burning. But eventually, everything is burned to iron. There's no more, nothing left to burn. The star is effectively all iron. And so gravity wins, and gravity collapses the star down. Now, the inside of the star collapses, but the outside actually explodes. When it starts to collapse, it collapses down, and basically the outer shell bounces off. Okay, and that's what we see. Okay, we typically see explosions. Here's another picture from Hubble of a nearby star that is blowing up. Okay. This is a nova. It'll do this many times in its lifetime. And then it puts gas and dust back into the universe, and then that goes around again and again and becomes more stars. Okay? And interestingly, by the way, the very first stars were only made out of hydrogen and helium, because the Big Bang only made hydrogen and helium. So where'd this carbon come from? All the carbon in our body, all the iron, was made inside stars. That's how we came here. Okay? It started out as hydrogen and helium. The very first stars converted that to iron and all the other elements, blew up, put it back into space, and then second generation stars could form that now could have planets and could have animals and people and machines and pointers and things like that. Okay, that's sort of an aside. So when the star explodes, it actually will end up as one of 3 things depending on how big it is. Okay? A really small star, like our sun, will end up in what's called a white dwarf, and it'll be about the size of the Earth. A bigger star has bigger gravity, so more forces pulling it together, and it'll actually be crunched down to something we call a neutron star, which is about the size of Santa Fe. And it's very dense because the sun, for example, is 1,000,000 times the size of the Earth. So, you know, you're going to crunch something 1,000,000 times the size of the Earth down into something the size of Santa Fe. And that's a neutron star, and it can be very stable and last for a very long time. But if it's a really big star, it has stronger gravity, which, by the way, means it evolves even faster. Is that a question? Or? Nope, it's a yawn. It evolves even faster, and when it dies, it produces a black hole which has 0 size. The gravity actually crunched itself down, to 0. So at the end of a star's life, the inside collapses because it's lost all its energy, but typically the outside blows off because it sort of bounces off the star as it starts to collapse. So, how do we make these black holes, and what does it mean to have like 0 size, and how does how does all the matter end up in something much smaller than that size right there? And before are there any questions before I go on to that?
Where's the iron?
Well, in this, actually, I'm not sure what the inside of this is. Here, all the iron has been pushed together and made into neutrons, and so this star is made only of neutrons. All the iron nucleuses and the protons have effectively decayed, and everything has been pushed into all neutrons, and you have effectively a nucleus the size of Santa Fe.
But that's iron.
Well, no, you no longer call it iron because it no longer has 26 protons and like that. It's now been all crushed into neutrons. Okay. Yes?
2 questions. How old is a star?
Well, some of these can be very young. Okay. These really big stars.
How old would a star be to make a black hole? It's humongous.
Well, because it's humongous, it evolves very quickly. So these can only be, just 10, 100 million years old. Okay, they only live for about 10 or 100 million years before they become a black hole. Our sun has been around for 5 billion years and will probably be around for another billion years before it turns into a white dwarf.
My other question was, when you measure the gamma rays, if you measure them and a star collapses, I mean, it's already collapsed by the time you're seeing the light.
Yes.
So how long does it?
It takes
time
about 10 billion years for those gamma rays to get here.
to get here? So
Yep.
it's been gone for 10
Yep.
billion years.
Yeah, oh yeah. We look in the past. When you look out in space, you're actually looking into the past because it takes a finite time for the light to get to us. We're seeing it. It's long gone. Yes.
Well, if stars are dying all the time,
Yep.
why don't we see more gamma rays coming out of the Milky Way and closer?
Oh, well, some of this, for example, this here happens about once every 100 years. Okay, I mean, in our galaxy with 100 billion stars, this happens about once every 100 years, and this ends up being a supernova. Okay, and the last visible supernova in our galaxy, Galileo saw it 400 years ago. Okay, there's been some other ones we haven't seen. This is somewhat more common. This type right here that's making the black hole is even rarer. Okay, there's probably 1,000 for every thousands of these. There's maybe one of these. Okay, so it's quite rare. And these gamma ray bursts have something about them that make them even rarer too, which I might be able to mention later on. Okay, any other questions?
If there's zero size, how can you detect them?
Oh, well, we'll talk about that. Okay. Okay, so what do we mean they have zero size? Well, first of all, thank you. First of all, we have to have some understanding of one way of looking at gravity, okay? And one way to look at gravity is you take space, like right here in front of us or any place, and you imagine there's a whole bunch of lines on it, okay? And what happens if you have no stars around, for example, a planet will move in a straight line, okay? So, everything will just move in a straight line. If there's no other masses around, no other forces, something that's moving just continues to move. Fine. Well, space is really like a rubber sheet. And what mass does is bends it. So here we have, I drew those lines, okay, so here's those lines again, except now we put a star in there, and the star has bent the space. This works out very nicely. This is Einstein's theory. This works out very nicely because now a planet still moves along a straight line. It's just that line goes around the star. If initially that mass is heading towards the star and moves along a line and collides with the star. But one way of thinking about gravity is, mass bends the space, and then other masses move along lines, certain lines that are around that space. So here's a space with no mass, and here's a space with mass. Well, one of the keys here is that there's more space there. Okay, just like if you took a rubber sheet and it was 2 feet by 2 feet, you put a bowling ball on it, now you have more rubber sheet. It is stretched. And that's what happens here. This mass has stretched the space, so there is more space there. Okay? So a black hole, the mass has been crushed down so small that it's actually stretched the space, so it has infinitely stretched the space. Forever and ever. So there's an infinite amount of space inside the black hole because it has stretched it so much. It has stretched the space itself so much. And, for example, since it's an infinite distance, infinite amount of space, it takes an infinite amount of time for light to get out of the black hole. And that's why we call them black holes. The light cannot get out of them. The light cannot get out of them, so we call that, that's why we call it a black hole. But since there's an infinite amount of space inside a black hole, you have this infinite amount of space, but that space might be able to fit in something maybe only a couple miles in diameter. The force of gravity is exactly the same far away from a black hole as it was before. Black holes do not suck. They have nothing special about them that's trying to pull things into them other than their gravity, which they had before. So right now, our planet is going around the sun, and we'll go around that sun for another 500 million or billion years. And if just right now, if the sun turned into a black hole, we'd continue to go around it for another 500 million or a billion years. There's no difference. The gravity is the same out here. We'll continue to go around it. Just we should all invest in tanning salons or something like that. So there's really no difference in the force of gravity sort of a reasonable distance away from the black hole. Now, very, very close to it, gravity does strange and different things, but far away from a black hole, it acts exactly the same as it did before. So the planet would continue to go around, our planet would continue to go around our sun, even if our sun turned into a black hole. Okay, do we have any questions?
Yeah, I have one.
Yes.
This black hole, the way you portrayed it, looks like it's going someplace.
Well, yeah, because this is a two-dimensional picture, okay? And this analogy with a rubber sheet is in 2 dimensions. But in fact, it's really in 3 dimensions. So you have to take a piece of space, draw 3-dimensional lines in it, a little grid, and then see that they really sort of crunch together this way. It's sort of a 4th dimension. So it's kind of hard to draw it on these figures here. This is the classic way of drawing it.
Well, my question is this black hole going out into a parallel universe?
No. No.
So there's no relation to that?
No, I don't think so. No.
Okay.
Okay, yes?
Is it truly infinite, or is it ultimately finite, but it's just that it's so...
No,
we can't measure it.
It's infinite.
It is infinite.
Yeah.
So
It takes an infinite amount of time for light to get out of it. Yes?
The center of the galaxy is a black hole, right?
That's correct.
So we would just keep orbiting it unless we exited before we got too close to it. Until we got sucked into it, the whole galaxy.
Well, black holes do not suck. No, they don't. No, they don't roll either. It's like any other mass. They just have gravity. And the gravity, well, only because it has gravity, but not because it's a black hole. I mean, if it was a large star with that much mass, then there'd be a large star that much mass, and things would go around it as the laws of physics say you go around, classic laws of physics, pre-Einstein says you go around it.
But the point being, everything in this galaxy will probably just get pulled towards the black hole.
No, I don't think so. Well, no, we're going to orbit around it.
So the black hole's not going anyplace?
Typically not. Typically the center, I mean, other things can go around them just like things go around stars. Planets go around stars. Stars go around the center of the galaxy. Yes?
Well, about the black holes going to another universe, couldn't it be that there could be another universe at the other end, but at the center the gravity is so intense nothing can get through?
Well, I don't think so. There's some people out there, and these are theoreticians, you can't trust theoreticians, okay? In my mind, there might be a theoretician in the room which I'm willing to be told, no, I don't know it. But I think what they do is they look at the equations, they see that the radius goes to 0, and they say, anything can happen. Maybe it's a wormhole, maybe it goes to some other universe. Now, I don't buy that myself. I think they're just, they're believing too much in that equation.
So it
Yes.
grows though? Does it grow? Or it stays at the same size?
Well,
It gains more mass?
it can gain more mass, and it can grow. And I think I forgot to use a term back here. We lost it here, or maybe I haven't said it yet. There's an infinite amount of space. I haven't talked about the event horizon, okay? So how big is a black hole? Well, the actual mass at the center has 0 size, but then we typically talk about the event horizon. This is the distance where on one side light can escape, and the other side the light cannot escape. And we call that the event horizon, and the event horizon has a certain distance. For example, if the Earth collapsed into a black hole, it'd be 2 inches in size. Okay? If the sun collapsed into a black hole, it'd be about 2 miles in size. So I don't know if I've answered your question. And more stuff can cause, if more matter falls into this, okay, because of its gravity, it does not suck, because of its gravity, then what happens is that this event horizon will get bigger. Yes?
I'm stuck on this size of the mass is 0, and I guess I relate gravity to mass. I can't imagine gravity without mass, and then you say there's mass, but it's 0, so I'm stuck here.
It's the size of the mass is 0. The mass is still there. It's still bending the space like it did before. Reasonable far distance away from it, it still looks like just a mass that you're going around, but in fact, it's bent the space and now has 0 size. It's stretched the space such that it takes an infinite amount of time to get out of it.
So it's not dark energy?
No, it has nothing to do with dark energy. Nothing to do with dark energy.
Purely mathematical?
Well, no, we see black holes. No, I mean, so.
It's mathematical.
Well, I don't think so. We see them. They're real. There's real black hole. I showed you a movie of a black hole. That film, I mean, that new star was a black hole being born. And it happens we see them about once a day. There's lots of black holes out there in the universe.
A new star being born was a black hole.
Yes. And I'll show a little bit more of that in a second here. Yeah. Okay. So it turns out black holes are at the center of the brightest objects in the universe. I know you're saying, yeah, but you just told me they were black. Okay, how come they're the brightest objects in the universe? Okay, well, let's look at this guy here. Let's say he weighs 400 pounds, and he's standing on the Earth, so he's 1 Earth distance away from the center of the Earth. The force of gravity depends on the distance you are from it. So, in fact, it depends on the 1 over the distance squared. So if this person went twice as far away, he would only weigh 400 pounds. 100 pounds, excuse me. If he went 3 times away, he'd weigh 44 pounds. Okay, because the force of gravity depends on the distance from the object as the distance squared. So, but if the Earth collapsed into a black hole, first of all, it'd be 2 inches in size. Okay? And now, if this 6-foot man is 6 feet away from that black hole, he would weigh 3.5 billion, the force of gravity on him would be 3.5 billion tons. Okay? Because d squared has gotten very small. That's the trick to why black holes are powerful. You can get very close to them, and so the force of gravity becomes very, very strong. Now, in fact, if you say his foot weighs 4 pounds, there's 35 million tons of force pulling on his foot. His head only has 8.7 million tons being pulled on the head. But look what's happening. Here's this poor guy has 35 million pounds of force pulling on his feet and only 8.7 million pounds being pulled on his head, so he's being ripped apart. Black holes rip everything apart as they get close to them. So that's why black holes are the brightest objects in the universe. Here's a black hole, like one at the center of our galaxy, and when a star is going around it, one side of the star has a lot more force of gravity than the other side of the star. And so stars are being ripped apart. The matter from that star is being accelerated to very close to the speed of light because it has this huge force of gravity because the black hole is small, not because it sucks, okay? Not because of anything else, just because the gravity is very small, is very strong because the d squared in the force of gravity can get very small. So that's why black holes are the brightest objects in the universe. They rip everything apart because of the difference of gravity on one side of an object compared to the other side of an object. Okay. So next I'm going to talk about, go back to the gamma ray burst and tell you how we think we relate these things. Yes?
And when you rip it apart, it emits the gamma rays?
No, I'll explain how the gamma ray bursts are made. They're a little bit different. This is what's typically happened in the center of many galaxies where stars are being ripped apart and they have very bright objects at the center of many galaxies. Like I said, black holes at the center of all the brightest objects in the universe. That particular case is stars being ripped apart.
So what makes them bright is the emission of...
Well, if you rip a star apart and accelerate its matter up to close to the speed of light and it's collided into things, you release a lot of energy. Okay, any other questions? Yes?
These black holes at the center of every galaxy?
Yes. Yeah, we think so.
You're going to explain why.
Pardon me?
You're going to explain why.
Well, on that topic? No, I think in most cases we think they're sort of the seeds. You know, in the very early universe, the black holes will form, and then since they have a lot of gravity, they'll pull other material. You know, other material as it goes around it will be pulled into it by normal gravity. They do not suck, and they grow very large. Okay, then there's sort of the seed that the rest of the galaxy forms around.
Now, you say that black holes are the center of every galaxy.
Pretty much, yeah, I think so, yeah.
So that's about the only place they are.
Oh, no, there's lots of stars around us that are black holes, too. That just happens to be these supermassive black holes. The black holes at the center of galaxies typically weigh 100 million times the sun, whereas black holes in other places around our galaxy maybe weigh 10, 30 times the mass of the sun. Yes?
Is everything going to go into the black holes?
At the end of the universe?
Yeah.
Maybe, yeah. Yeah, the question was, will everything eventually go into a black hole? And if by eventually you mean a time that we can barely write down enough zeros about, I think that's true. Yes?
Does everything revolve around a giant black hole?
No. Most things are in galaxies, and therefore they're going around the center of that galaxy, which is a black hole. But even within our own galaxy, there are processes which kick stars out, and they can actually escape from the galaxy. So they're very rare, but you can kick things out of the galaxy. Google can find it, yeah. Have I written a book on this? No. But as a commercial, one of the things I actually retired from the laboratory, which means I'm trying to cut back to 40 hours a week. And the thing I do in the other time is I go to speak at schools, so particularly 6th grade, 7th grade, around that time. So if you have any school teachers, I'd love to come to your school. We're ready to go? Okay. So now we want to talk about gamma ray bursts and how they are powered by a black hole. Just after the Big Bang, the stars that formed are different than the stars that are being born today. After the Big Bang, there was only hydrogen and helium. And it turns out, if you try to make a star out of hydrogen and helium, you make very large stars. So since it's a very large star, it evolves very quickly, and it ends up being a black hole. Nowadays, there's enough carbon and nitrogen and other things in the universe that the way stars form, they end up being smaller. So that's why we don't have gamma ray bursts in our galaxy being made today, because we don't have the size stars that the very first stars in the universe were. So here's how we think gamma ray bursts happen. Here is a star that's spinning. Maybe it's 10 to 100 times the mass of the sun. It has evolved very quickly. It was one of these early stars that were only made out of hydrogen and helium, but by now it has burned all that hydrogen and helium up to iron. It has no more material in which to generate energy, and gravity is going to win. Okay, gravity is going to take this and it's going to collapse it into a black hole, but part of it will bounce out. Now, and if you look at this in some directions, it'll look like a supernova. Okay? But if you just happen to be lined up with that spin axis of the star, that along that axis, this is a computer model of how the collapse occurs, and it ends up, as the collapse occurs, because it's spinning, it ends up producing a jet of material. Most of the material is falling into the black hole, but some of it is sort of squirting out the edges, squirting out along the spin axis. And in fact, it's moving very close to the speed of light. It's moving maybe 0.99 the speed of light. So what happens is little blobs of gas come out. Now, when I say little blobs, I mean maybe 10 times the mass of the Earth. But they're moving at 0.9999 the speed of light. They have a tremendous amount of stored energy. And just like on I-25, there's somebody moving 0.9998 the speed of light. Okay? And they get rear-ended by the people, the other ones in a hurry that are moving even faster, 0.99999. So what you end up happening is that these blobs of things coming out along this spin axis are these huge masses, 10 times the mass. It's like having two cars moving very close to the speed of light that weigh 10 times the mass of the Earth plowing into each other. Okay? When you have such a collision, you produce a lot of heat, a lot of energy, and that's what's making the gamma rays. So here we have a short movie that shows that. We need to do something here to get it going. So here are these blobs coming out, and every time two of these blobs hit each other, they make a burst of gamma rays. Okay? They make a burst of gamma rays until finally there's just one shell moving out. But here, you notice we have this train of 3 pulses, 2 pulses, then some other pulses. And that's what we see as those gamma rays. That very first movie I showed you, which showed you all those spikes, each one of those spikes was 2 of these blobs running into each other at very close to the speed of light. And once they collided, just like in a car crash, you produce a lot of heat, a lot of energy. Same thing here, you collide these two things together, and you end up producing these pulses that made the gamma ray burst. Earlier, we had seen that in that movie I showed, which showed that one sort of new star being born. That's this optical light that comes out very late. At the time about this view-graph was being made, the Swift satellite had just been launched, and the Swift satellite discovered several things, including how it connects together and the fact that you still get these pulses later on, which told us that the process of making this black hole actually lasts much, much longer than we thought it did. Originally, we thought it lasted, I can remember when I was working on these things many years ago, we thought it occurred in milliseconds. Okay, and now we realize, no, we're only off by 6 or 7 orders of magnitude, that it actually can take 10,000 seconds or so for all this activity to continue. Now, black holes explain one type of gamma ray burst. There's another type that I'd just like maybe to show quickly. There's some short gamma ray bursts. This is one that we saw. This is really an amazing event. In this case, here's an initial spike, a huge spike, but we've cut that off so you can see this. Something turned on and made all these pulses. And there's a bright pulse, dim pulse, bright pulse, dim pulse, bright pulse, dim pulse. Now, this is very, very bright. In fact, this was seen with the Swift satellite. And when we designed the Swift satellite, this is about the maximum number of counts that we designed Swift to see. Okay, because we estimated what's the biggest gamma ray burst we're going to see. Okay, we'll build this thing to handle the biggest gamma ray burst we could see. And this spike was bigger. In fact, it's so big that I'd have to have a screen a half a mile tall to show it to you. Okay, this was a surprise. Okay, this was many, many orders of magnitude brighter than we had ever seen before. And in fact, there was so much energy that it hit the Earth with what a physicist would call 5 ergs per second per square centimeter, but that's equivalent to a dime hitting every square inch of the Earth at about 2 inches per second. So it actually had an effect on the Earth's atmosphere. It certainly had an effect on the Earth's ionosphere, and this was a huge event.
When did that happen?
This happened December 27, 2004. The fact that it was the day after the tsunami is just a coincidence. The tsunami, the big earthquake. But it is interesting because we think it was made by a starquake instead of an earthquake. Here is a model of a neutron star. And neutron stars can have very, very strong magnetic fields, just incredibly strong magnetic fields. In fact, if you take a little volume that's empty, it's a vacuum, okay, except it has this magnetic field. Well, the magnetic field has a certain energy density, and just a volume equal to a poppy seed actually contains a year's supply of energy for the United States. There is so much energy in this vacuum that even a cubic inch, because E equals mc squared, looks like it weighs 16,000 tons, even though it's a vacuum. Now, neutron stars are very solid. They actually have a solid crust. And this thing is spinning, and then star quakes occur on it. It reorganizes the magnetic field, releases a huge amount of energy, and then you see a bright spot, a dim spot, a bright spot, a dim spot, and sort of like a lighthouse going around, making these spikes that we saw. So we saw that initial big spike that goes up a half a mile, and then we see all these subsequent spikes that occur. So here's a summary. Gamma ray bursts, which are black holes being born, are the brightest objects in the universe. Also, they hold the record for the furthest thing ever seen. All these great telescopes they have on the Earth, our Swift satellite beat them by a huge amount. We have found a gamma ray burst at 13.3 billion light years away, and the universe is only 13.7 billion years old. So it's the furthest object. It's one of the very first stars ever formed. Mass bends space, so there's an infinite amount of space inside a black hole, but it has huge differences in the gravity near the black hole, and that's what makes them the brightest objects in the universe. And then, of course, science is great fun if you get to work with satellites and telescopes and trying to figure out all these things. Okay, thank you. Did you have a question?